order observables that we can look for. I'm then going to move into what's going to be the meat of the presentation, how we actually can observe this planetary 3D-ness, starting off with what is really the gold standard, right? Phase curves. And then how can we do 3D observations without needing full orbit phase curves? Things like transit limb asymmetries, which is what I'm going to focus the most on. And then also, if we have time, moving a little bit into what we can do with eclipse mapping as well. And then we'll wrap up with the conclusions. Okay, so starting off with the theory, and I'm going to preface all this by saying that I primarily am an observer, right? And so I am definitely not an expert in GCMs here. There are many, many other much better experts in GCM modeling attending this talk. So if you have any problems with what I'm saying, please bring it up to them and don't yell at me about this. But I'm going to try to give you a kind of first order explanation of the major things that we can learn from GCMs that are important if we want to understand the 3D-ness of giant planet atmospheres, and then also link these back to actual observables that we can extract from our observations. And so the first thing that we need to start off with, right, what are GCMs doing ultimately? Well, they're kind of coupling both the circulation, the chemistry, and possibly even cloud and aerosol formation in planetary atmospheres in order to get a global understanding of that planet's atmosphere, all ultimately rooted in what we think we understand about atmospheric physics and atmospheric chemistry. And ultimately, right, these models are based in planetary astronomy and in understanding of the Earth and understanding of the other giant planets in the solar system. And these are in some ways more difficult cases than actual exoplanets. And the reason for that is because winds and climates in the solar system can be quite messy, right? We know that simply just from everyday weather and climate on Earth. Things are very rapidly varying on timescales that we simply could not even hope to resolve on an exoplanet. And so, for example, in this little schematic of major wind patterns on the Earth, right, we have Hadley cells, we have other different circulation cells. And if we look at Jupiter, right, things get even more complicated because Jupiter is rotating faster than the Earth is. And so the wind cells break up into much smaller structures than they do on the Earth. However, if we kind of go to the exoplanet regime, and this is one of the first GCMs that was then applied to a hot giant exoplanet that I can find, which is from Showman and Gio in 2002, right? And here we see kind of a different regime emerging, right? Because our hot giant exoplanets are very externally forced, very highly irradiated from their host star. They're also tidally locked, right? So we have that permanent day side and permanent night side, which is clearly a very different regime than we have here on any planet in the solar system. And so the wind patterns that GCMs tend to give out for these sorts of planets are very different than what we just saw for the solar system planets, right? One of the major things that we have here is a prominent east-west flow, right? So heat being recirculated from that permanent day side around to the permanent night side around the equator. And we have much less day-night heat recirculation. So that's just kind of a general flow from the day side to the night side, as opposed to directly with that so-called equatorial jet. And this is a very robust prediction of GCMs across a wide range of planetary temperatures. This is some of the kind of foundational work in this regime from Tiffany Kataria in 2016. Right, where we see going from temperatures on the order of 700 Kelvin up to nearly 2,500 Kelvin. So we're looking at a range of temperatures almost spanning 2,000 Kelvin, and we consistently see in the deep atmosphere, right, this is on the order of 100 millibars, right, that the dominant flow is that east to west equatorial jet. And so one of the first major observable outcomes of this, and I'm going to put kind of major observable outcomes that we should be keeping in mind for the rest of the talk on slides in blue, is that this kind of bulk east to west flow should result in the hottest part of the planet being shifted east from the substellar point. And especially in the case of these hot planets on the bottom row, WASP 31b, 17b, and 19b, you can really see that the bright yellow parts, the hottest part of the planet atmospheres, are always shifted to the right or to the east of that substellar point at zero longitude. Now, the picture gets a little bit different as we move up in the atmosphere, more to pressures that we're probing in transmission. So what we've been talking about previously has all been the deep atmosphere. But now if we move up from, let's say, a few hundreds of millibars up to now a fraction of a millibar, what we see in both of these plots from Flowers et al. In 2019 and from some of Maria Steinwerk's work in 2023, that as we move to the upper level panels, right, that east-west jet seems to disappear. And what we get is more instead that bulk day to night flow as opposed to the equatorial jet. So the day-night flow instead becomes more dominant in the upper atmosphere, whereas it's that jet that is more dominant in the lower atmosphere for giant planets. Now, another outcome of this 3D circulation is that these day, night, and east-west temperature differences can also drive differences in cloud formation. And a really nice example of this is work from Vivian Parmentier in 2016, where we see a suite here of GCMs of planets of different temperatures in each row, ranging from about 1100 to 2100 Kelvin. The top row is showing just the temperature at 10 millibars. The second is showing the emission from a cloudless planet. And this is all, I want to note, in the Kepler bandpass, and I'll get to why that's important in a second. And then the final 4 rows are all the emission in the Kepler bandpass if we allow clouds to form with different compositions, with CaTiO3 down to Na2S at the bottom. Now, the reason the fact that this is the Kepler bandpass is important is because Kepler observes quite blue. The result of this is that you get both a mix of thermal emission and reflected light in the Kepler bandpass. And so what we can immediately see, for example, if we take the 1900 Kelvin planet as an example, right, is that the temperature at 12 millibars, what do we see? Well, again, we see the hottest part of the planet is shifted east to the right of the substellar point, right? This makes sense from what we discussed previously. And if we look at the cloudless planet atmosphere, where's the most emission coming from? Well, the most emission is coming from where the planet is hottest, the eastern part. Again, this makes complete sense. Well, now what if we allow clouds to form? Well, let's take the first example with CaTiO3 clouds. Now, all of a sudden, we see that the most emission is actually coming from the western hemisphere of the planet. Well, what's going on here? Well, again, recall that I said the Kepler bandpass is a combination of thermal emission and reflected light. So we're getting actually a lot of reflected light from the colder western hemisphere, which allows clouds to form. Highly reflective clouds add a lot of emission to the Kepler bandpass, actually dwarfing the contribution from the thermal emission on the eastern hemisphere. So a key kind of observational takeaway from this, once again, is that this asymmetric cloud formation, this asymmetric temperature in a 3D planet atmosphere should result in a cloudier and more reflective western hemisphere as opposed to an eastern hemisphere. And finally, we can also think about the effect of the 3D-ness of a planet on atmosphere chemistry. And this is from some work by Maria Zamiatina in 2024, where we did some GCM modeling of, in this case, WASP-96b, assuming a solar chemistry, a solar metallicity atmosphere, and looked at the abundance of methane if we just let the atmosphere sit in chemical equilibrium, or if we also include the effects of 3D mixing. And what we saw is that in the plot on the left-hand side, right, where we have just a solar metallicity chemical equilibrium atmosphere, on the hotter evening, we see much less methane, that's these brighter colors, than we do in the colder morning, right? That makes sense. Methane is going to be more dominant over things like CO when the atmosphere is colder. However, if we now let kind of mixing equalize the abundance of methane throughout the atmosphere, we find a much more consistent intermediate abundance of methane. And that might actually lead to detectable amounts of methane in the transmission spectrum of this planet, where there wouldn't be if it was just simply a planet in chemical equilibrium. And once again, now the plot on the right-hand side is showing those differences where if we allow for that 3D mixing from morning to night, we find much more methane on the evening and less methane on the morning because it's equalizing over the whole planet. So again, another key observational takeaway is that atmosphere circulation is going to drive chemistry away from what we would just simply expect with equilibrium chemistry expectation. Now, just to quickly summarize what we've talked about in this theory section, some of the main links to observations. Once again, the hottest part of the planet should be shifted eastwards from the substellar point. The Western Hemisphere should thus be colder, cloudier, and more reflective than the Eastern Hemisphere. And finally, as we just discussed, the atmosphere circulation should be driving chemistry away from that simple equilibrium expectation. Okay, so now that we have kind of an idea of what sort of things that we should be looking for in our observations, let's now talk about how we can actually go about observing these sorts of effects. And I'm sure most people here don't need this explanation, but just in case and just to make sure we're all on the same page, I'm going to quickly review the major techniques that we can use to observe exoplanets, starting off with the transit, which of course is when the planet is passing in front of the host star as seen by an observer on Earth or a telescope up in space. We also have the eclipse, which is when the planet is passing behind the star, and now the thermal emission from the planet is being hidden by the star as it passes behind. And finally, we can also obviously observe the planet throughout the entirety of its orbit using a full orbit phase curve. And if we really want to observe the 3D nature of an exoplanet, obviously a phase curve is going to be the gold standard, right? We can actually see the difference in the planet, difference in its chemistry, difference in its reflectivity, thermal emission, etc., as a function of longitude. And so this really makes, like I said, phase curves the gold standard for observations of 3D exoplanets. And the first time that we tried to do this was with HD 189, I believe, from Heather Knudsen in 2007, right? And this is an example of a phase curve that we would see with Spitzer. We see on the top panel, right, we have the full phase curve, and the bottom is zoomed in so that we can see the planet's thermal variation. So at phase 0, we have the deep planetary transit. Phase 0.5, we have the eclipse. And then in between those, we see that sinusoidal variation in the planet's thermal emission as more of the day side rotates into view. Another interesting fact about this phase curve, right, is because it was the very first, if not one of the first, right, in order to save time in the observations, we're normally used to seeing 2 eclipses bracketing the phase curve, but in this case, in order to save time and have a better chance of the observation actually getting accepted by the TAC, right, only 1 eclipse was observed. And this obviously does introduce some more difficulties in reducing the data and fitting the phase curve, but we can still quite clearly see the planet's thermal variation. And what this phase curve then allows you to do, right, is invert it in order to get a map of the temperature on the planet's surface. So an important thing to keep in mind here in this panel A is that kind of the latitudinal information here is mostly made up. The actual longitudinal information, though, is what we can infer from the phase curve. And what we see both in the top panel in that map and also in the bottom panel, where we have the relative brightness as a function of latitude, is that we see the brightest part of the planet is again shifted east from the substellar point. Exactly, again, what we would expect from our theory if the bulk flow is east to west. Sorry, west to east. And so, yeah, we have the hot spot shifted east of the substellar point. Now, most of the phase curves that we took in kind of the pre-JWST era were photometric phase curves, either with Spitzer in the infrared or with Kepler or TESS in kind of the optical regime. And one of the problems with photometric phase curves, especially in the optical, is it becomes very difficult to disentangle the impacts of reflected light and thermal emission with just one single observation. And kind of a great example of this, right, is some of the work that Vivian did with Kepler phase curves, right? And here we have an example where the black line here is showing the total emission from the planet as a function of phase. And this is being semi-decomposed into components of reflected light, shown in blue, and thermal emission, shown in red. Right, and we have thermal emission peaking on the eastern hemisphere pre-zero phase, and we have the reflected light dominated from the western hemisphere, which again should be cloudy. However, this is very difficult to do with just one single photometric phase curve. And this is really an area where JWST is changing things, because with JWST, we can get much better spectroscopic coverage at much higher precision across this kind of optical to near-infrared waveband. And a key example of this is work that Louis-Philippe Coulomb and myself did with the ultra-hot Neptune LTT 9779b, which was published earlier this year. And so this degeneracy between thermal emission and reflected light can really be broken with JWST, especially with instruments like NIRA-SOS or with NIRSpec and prism mode, because we have spectroscopic coverage of both wavelengths dominated by reflective light and more of the optical, and wavelengths dominated by thermal emission in the infrared. And so we observed a full orbit phase curve of LTT 9779b with NIRA-SOS. And what we can see on the right-hand side, we have the reflected light contribution to the phase curve. And on the left-hand side, I guess it's switch for you. Yeah, so the right-hand side, we have the thermal emission contribution to the phase curve. And the left-hand side, we have the reflected light contribution to the phase curve. And what we can see is that with the reflected light, we're basically peaking in the Western hemisphere, whereas the thermal emission seems to be centered more or less around the substellar point with maybe a very slight shift to the east. And once again, this is exactly what we would expect from theory, right? We should expect the thermal emission to come from the hotter Eastern hemisphere, and we should expect the Western hemisphere to be colder, cloudier, and therefore more reflective. And this is exactly what we're seeing in these observations. Now, I also want to add a note for completeness that phase curves can also be used, right, to disentangle whether or not there's an atmosphere on potentially rocky planets. And this is one of the first examples of this from Laura Kreidberg's work on LHS 3844b, where with the phase curve, right, if there is an atmosphere, then we should expect some of that heat that's impinging on the day side to be recirculated to the night side of the planet. However, if there is no atmosphere present, then we should expect to see a night side that's as cold as it can possibly be, and a day side that's as hot as it can possibly be. And so that's exactly what they found in this case for this planet, a very, very, very hot day side and a very cold night side, suggestive of no heat recirculation and basically no atmosphere. And I also promise that this will be the only rock that I'm going to show in the entirety of this slide. I just wanted to mention for completeness that we can also use phase curves to probe the presence of atmospheres via kind of the 3D circulation of heat. Okay, well, phase curves, right, naturally require you to observe an entire orbit of a planet. So for ultra short period things with periods less than a day, right, that's a semi-reasonable ask to make to attack, right? If you only need on the order of 24 hours to observe an entire orbit, you can make a very cogent argument that the amount of science you're going to extract from this phase curve really is a motivation to get these very time-intensive observations. However, what if you want to push to slightly colder and longer period planets, something maybe with a period of 3 days, or you even want to push to warm or cooler planets, which have much, much longer periods? Personally, I think it'd be very difficult to get, a 10, 20-day phase curve past a JWST TAC. That is quite a lot of observing time for one singular phase curve. So as observers, right, we've had to come up with different ways that we can probe the 3D nature of exoplanets without really requiring an observation of one full orbit. And so I'm going to move into that now, and I'm going to say this slightly tongue-in-cheek, right? Options for the impatient, right? What can we do if we don't want to observe a full phase curve? But maybe options for the impatient isn't necessarily the best way to put it. Maybe options for TACs, which are slightly too picky and don't want to give long period observations. But either or, what sort of things can we do to observe 3D atmospheres around planets if we aren't able to get a full phase curve? So the first thing I'm going to talk about are transit limb asymmetries. And just so that we're all on the same page, and again, I'm sure most of you won't need this review, but for those of you who aren't familiar with asymmetries and how they work, basically, from all the things that we've discussed about 3D planets, from heat recirculation, we think about our standard 1D planet assumption, right? We have a spherical planet or a circular planet if it's projected in transmission, and we have a perfectly spherical or circular annulus of an atmosphere around that planet, where the basically size of the atmosphere is the same on the day side, the night side, the morning, and the evening. Well, from everything that we've now talked about with the possible 3D circulation of heat around a planet's atmosphere, we know that this probably isn't actually an accurate representation of the planet's atmosphere, right? The day side should be hotter and therefore puffier. The night side should be colder and smaller. Similarly, the evening should be hotter, the morning should be colder, and this should lead to a much different shape of the planet's atmosphere if it is indeed truly 3D, right? We have a hotter, puffier day side, colder, less puffy night side. So the first thing we might think to do is say, okay, can we directly see this day-night difference with just our standard transmission spectrum, right? Because light passing through the atmosphere is going to sample both that hot day side and that cold night side before reaching us on Earth. Well, luckily, Jonathan Fortney has actually explored these possibilities way over a decade ago now in 2010. Right, and this is an exploration of this exact same effect for HD 209, right? Whether we can possibly disentangle the effects of the day side and the night side with just one simple transmission spectrum. And unfortunately, for most planets, this measurement is going to be very difficult. The reason for that is this full model transmission spectrum, which has both the contribution of the day side and the night side, is basically entirely dominated by that hotter day side. There's effectively no difference between the day side and full model, whereas the night side contribution is entirely dwarfed. So for the vast majority of planets, right, it's going to be very difficult to disentangle day-night differences with just your standard transmission spectrum. Okay, well, what if we do something slightly different? What if we think about disentangling the effects of the morning and the evening? Well, here we can actually use the fact that the ingress of the transit probes primarily the colder morning hemisphere of the atmosphere, whereas the egress is now probing the hotter evening hemisphere. And so if we can find a way to kind of isolate the contributions of the transit ingress and the transit egress, and we can potentially disentangle, right, the effects of the morning and the evening hemisphere. And let's go back to Jonathan Fortney's work and see maybe if this is a more promising avenue to access the 3D differences in planet atmospheres via transmission spectra. And indeed, in this case for HD 109, we see much larger differences between the morning and the evening hemisphere, in this case, the leading and trailing limbs, which he's called them, where we see much larger spectral features in the hotter evening than we do in the morning, and in general, deeper transit depths in the evening compared to the morning, due to the fact that the atmosphere is hotter and puffier. So this is promising, but is this something that we can actually observe? Well, in the pre-JWST era, probably not, and I'll talk a little bit more about that later. But now with JWST, we have such precise light curves that we can actually think about disentangling the effects of the morning and the evening. And let's talk quickly about how one might go about doing this. There are three main techniques that I want to cover, and there might be more that I'm unaware of or I'm not going to focus on here, so I apologize if I miss your favorite technique. But the first one, and probably the simplest, right, is simply fitting only integrations that correspond to the morning and only integrations that correspond to the evening, right? So if we say that these integrations in ingress are for the morning, these integrations in egress are for the evening, and we fit only these integrations by themselves, then in theory, we can get out a transmission spectrum of the morning and a transmission spectrum of the evening, right? But a problem here is that there's a lot of the transit that we're not using. And so our error bars and our precision is naturally going to be much lower than if we found a way to make use of the entire transit. We have other ideas, for example, transmission strings, which was a wonderful idea from David Grant and Hannah Wakeford a few years ago, which I think warrants a little bit of a deeper dive. And the idea behind transmission strings ultimately is that you can fit your transit light curve, right, using kind of a Fourier series decomposition, which allows you to kind of map the kind of radial extent and radial shape of the atmosphere as a function of wavelength. Right, and so in this little middle panel here on the screen, you can see the effect of this on some simulated data, where you see a hotter, puffier, what I'm going to assume is the evening hemisphere, and a colder, smaller morning hemisphere, which can potentially pop out through transmission string fits. Now, the final technique, which I think is the one that's been most widely adopted by the community, is fitting what I'm going to call an asymmetric transit model to the entire light curve. And this is kind of primarily done with a Catwoman model from Jones and Espinoza a few years ago. And one of the big benefits of this method is that it uses the entirety of the transit light curve. And another big benefit is that the bar to entry, right, for this is very low. Effectively, you're fitting the same Batman model that you would normally fit to your transits, but you're adding an extra parameter to allow for an asymmetric transit. And to show what I mean by this, we look at this schematic from Nestor's paper last year, where we see for the symmetric transit with their normal Batman model, we're effectively assuming that we have a perfectly circular transit annulus for the atmosphere, which is the same in the east as it is in the west. Now, we just break that assumption when we use a Catwoman model and we fit an asymmetric transit. What we do instead is we use two different occulting semicircles, which can potentially have different radii if we find that the evening, for example, is hotter and puffier than the morning. Now, a kind of key difficulty with this technique is that the residuals, right, that we expect between an asymmetric and a symmetric transit are quite small. Right, I think I'd be very skeptical, right, if you just simply looked at these residuals and told me without a doubt that the asymmetric transit definitely fits better than the symmetric transit. The differences are primarily going to be during ingress and egress, right, which is also generally where we have fewer points because ingress and egress are much shorter compared to our baseline or compared to the transit itself. But the fact that these residuals are very similar between the asymmetric and symmetric transit, and also quite small, is one of the main reasons why these techniques and these sorts of transit asymmetries were really beyond the capabilities of HST. Right, let's take a look at some of the best things that HST can do. This is from some of Hannah's work a few years ago, where we see HST white light curves from 3 different visits. And so not only are the residuals much bigger than we get with JWST, we also have much fewer points in transit ingress and egress, which is, again, where most of those limb asymmetry signatures are going to be imprinted. And we have these giant gaps in observations due to the telescope being occulted by the Earth. So it was very, very difficult to actually get out any sort of signature of limb asymmetries with HST. I'm actually not 100% sure if there was any claim of limb asymmetries published in the pre-JWST era. And so really these limb asymmetries were a pipe dream before JWST came. But now with JWST, we have a whole bunch of different success stories of actually being able to detect limb asymmetries in exoplanet atmospheres. The first being everyone's favorite WST-39b with near-spec prism. This was Nestor's work published last year, where we see a hotter evening hemisphere where the transmission spectrum is generally shifted upwards from the colder morning. We have this great spectrum of WST-107 from Matt Murphy's work last year as well. This time with NIRCam, where again, we see a puffier, hotter evening hemisphere with larger spectral features compared to the morning. But I think even more remarkable than this NIRCam work is the panchromatic work that Matt published earlier this year, where now we see limb asymmetries not only in NIRCam, but across all 4 of JWST's instruments, with NIRISS, with NIRSPEC, with NIRCam, and with MIRI. And so in the near infrared, what we primarily see, right, are hotter, larger spectral features in the evening compared to the morning, not much different from what we saw with NIRCam on the previous slide. But I think what is even more remarkable is if we now go into the mid-infrared with MIRI, we see now a massive feature in that colder morning, which is not really present in that eastern hemisphere. And we think this feature is actually due to the formation of clouds, where we see clouds forming on the colder morning, and we see a now cloud-free evening hemisphere. And so this is kind of very complementary to, for example, what Louis Philippe and myself did with LTT 9779b, where instead of now looking at reflective light, here we're kind of directly detecting the cloud species in the mid-infrared, but still painting that same picture of a cloudier morning and cloud-free eastern hemisphere. And finally, I also want to point out this really cool result, which is kind of along a similar line from Shagnik a few weeks ago for WST-94AB, again using NIRISS, where they find a very flat, slightly slopey, aerosol-heavy morning hemisphere and a evening hemisphere where we now see spectral features and is basically entirely cloud-free. So I want to now change a little bit to talk about WASP 96b, which is something that I've been working on quite a lot recently. And this fits kind of quite well with our limb asymmetry discussion, because if you know something about WASP 96b, it's generally that, the planet has been claimed to be cloud-free. And this really comes from observations from the VLT, which showed very broad sodium wings, and led to, yes, this claim that the planet likely has no clouds in its atmosphere. But this has always not made sense to me, and I think a lot of other people as well, right? Especially for a 1300 Kelvin hot Saturn sort of planet, how can it be possible that we don't have any clouds in this planet's atmosphere? But a potential solution to this, right, is that we simply have the transmission spectrum being dominated by the contribution from the hotter, puffier, cloud-free evening hemisphere, but we still do have clouds forming on the morning, but their contribution to that limb average transmission spectrum is simply being dwarfed. And we already saw some indications that maybe this cloud-free picture of the planet is breaking down with JWST observations using near a sauce that myself and Jake Taylor published 2 years ago, where we see when we compare the data in gray to cloud-free GCM models and the colored lines, that we match very well in near infrared, right? We basically have no contribution from clouds. But as we move into the optical wavelengths, and we can expect maybe scattering and reflection from clouds, there's clearly some missing opacity. So maybe the kind of cloud-free story for this planet is starting to fall apart just a little bit. JWST observations also show, or sorry, in this case, GCMs also show that cloud formation is entirely possible on the morning hemisphere. These are some GCMs that Duncan has run recently for WASP 96b, assuming a 10 times solar metallicity atmosphere. And if we look at just the profiles of the morning hemisphere, they're cold enough to allow for formation of Na2S or even KCl clouds, whereas the hotter evening hemisphere seems to be mostly cloud-free at those kind of millibar or higher pressures that we should be probing in transmission. So once again, it could simply be that our average spectrum is dominated by that cloud-free evening, and we just are sensitive to the contribution from the cloudy evening. And finally, one thing that Maria has predicted previously is that detectable levels of methane could also be present in this planet's atmosphere, as we saw on previous slides, right? If that 3D homogenization is occurring between kind of a methane-heavy night side and a methane-poor day side. In order to test all of these different things, Jake and I went out and got some additional JWST observations of this planet using the NIRSPEC instrument now, hoping to kind of resolve this cloud question and also see whether we can detect the signatures of methane, which would suggest, right, 3D homogenization of that that molecule's abundance. And so before we even talk about limb asymmetries, we can really see that even with the additional NIRSPEC observations, and even when we add in the ground-based observations, this is just that limb average transmission spectrum, that we're really breaking that cloud-free claim about the planet. All of our models require some sort of aerosol, be it a cloud, be it a haze, we can't quite say, but cloud-free models just are not able to fit the combined transmission spectrum for this planet. We can't say, right, whether it's a haze or whether it's a cloud, because ultimately what we really see is just an aerosol slope. We don't, though, find any evidence for methane in the spectrum, though the atmosphere metallicity that we find is slightly higher than we had initially found with just the SOS observations, which was a solar metallicity atmosphere. We find about a 10 times solar metallicity atmosphere, in which case methane is already going to be more depleted than it would be with just a solar metallicity case. And so even if the methane is being homogenized over the entire planet, it still might fall below our detection threshold with these observations. And now if we want to look at the actual limb spectra themselves, which were extracted with that asymmetric transit Catwoman method, there's a couple of very interesting things to note. The first is that there are really no evidence for limb asymmetries in the near spec band. So that is from our 3 to 5 microns, where now on the top panel, right, I'm highlighting the contribution from the morning in blue. And on the bottom panel, I'm highlighting the contribution from the evening in red, but still showing both the evening and the morning spectra and faded points in the top and bottom respectively, just so you can compare. And so don't necessarily pay attention to the retrieval model shown in blue, or sorry, in black. But if we look at the near spec bandpass, right, there really doesn't seem to be any difference between the morning and evening spectrum. They're basically always lying right on top of each other. But if we go to the nearest bandpass, and particularly that kind of window from 1 to 2 microns, we see a much flatter morning spectrum and an evening spectrum that seems to have evidence for spectral features, very reminiscent of what Chagnick saw in WST94AB. And so perhaps we have some evidence for a cloudier morning hemisphere and a cloud-free evening hemisphere, just as we predicted. However, these limb asymmetries, these limb differences aren't really as large as previous examples that we saw, but this might actually be good news. And the reason for that is that GCMs have generally struggled to match observed limb asymmetries. An example of this is work that was done for WST39b as part of Nestor's paper in 2024, where we see, regardless of whether we include transport-induced chemistry, equilibrium chemistry, clouds, hazes, etc., the GCMs always predict smaller limb asymmetries than were observed in WST96b. And so, or sorry, in WST39b. And so here in WST96b, we see differences on the order of 1 to 2 scale heights, which are much more in line with the sort of things that GCMs are actually predicting. But the question becomes, especially for cases where the limb difference is borderline, right, are these observed differences actually real? And so we can take a couple of different approaches to figure this out. The first of which is kind of doing a Bayesian evidence comparison between a asymmetric transit model and a symmetric transit model. So with this test, I find that in order for us to get a significant detection, like a 100 to 1 odds ratio in favor of an asymmetric versus symmetric transit, we would need limb differences on the order of 6 scale heights for nearest and 9 scale heights for near spec. But the differences that we see in the data is on the order of 1 to 2 scale heights. So this would suggest that these differences aren't significant. However, if we take an alternative test where we now see what are the chances, right, of these limb asymmetries arising just by random if there is no underlying limb difference, well, after 10,000 injection recovery tests, basically the differences that I see arose almost never. And so we would say that from kind of a frequentist standpoint, that this is kind of a 4 sigma significant detection. And one of the reasons why kind of doing a number of different tests and really trying to figure out whether limb asymmetries are real can be summarized again with this WST94AB work, where Chagnick had this claim of clear limb asymmetry detections with nearest sauce. They did kind of the normal barrage of tests to make sure their transit spectra were robust, but not much that was very specific to really making sure limb asymmetries were present. But on the other hand, Evie published on the same day, right, a near spec transmission spectrum of the same planet, but did what are arguably maybe more robust tests for limb asymmetries and found the Bayesian evidence always preferred the symmetric transit model. And so although by eye, right, it looks like there are limb asymmetries present in this data set, they chose to take the more conservative route and say that there wasn't any really strong evidence for limb asymmetries and kind of left that for later work. So it's kind of important, right, that as a field, we come to, I guess, a method that we can have to say whether or not the limb asymmetries we have in our data are truly real or not. And so one of the things that I'm kind of going to propose here is that we take an ensemble approach to this, right? In the case of, is there methane present in my retrieval, right? The community has settled on a pretty standard approach to actually say whether this is true or false. But I think this is lacking a little bit in the area of limb asymmetries. And so I'm going to propose here, just to quickly end off, a handful of different tests with increasing complexity, increasing robustness, perhaps for actually ascertaining whether potential limb asymmetries that one sees in their data are in fact truly real. The first is simply doing the same gauntlet of tests that you would normally do for your transmission spectrum, right? If you think you see methane, you would do, or the referee will probably tell you to do when you submit your paper, right? Seeing whether your transmission spectrum changes or your detection significances change if you fit using different limb darkening, if you fit T naught, etc. So doing all those normal things that you would do for your transmission spectrum and seeing whether your limb asymmetries go away or not. The second is looking at whether or not your limb asymmetries make sense physically, right? Are you finding that the eastern hemisphere or the evening is actually cloudier but yet warmer, right? Do things make sense physically? That does what you're seeing make sense physically? Thirdly, is the polarity of the morning and evening spectra constant, or does it constantly flip-flop back and forth? Right? If you're constantly finding that the evening is deeper, has a deeper transit than the morning, right? This is more likely to be true than if they're basically overlying each other and the points for the morning and evening are constantly flip-flopping back and forth. Finally, we can start doing some much more robust statistical tests, right? We can take a frequentist example of this, like I showed on a previous slide, right? If we assume no underlying limb asymmetry and do injection recovery tests, are we actually able to reproduce the observations, or do we always see our observations having more limb asymmetry than we could possibly see if there was nothing in the underlying data? And finally, we can do these Bayesian tests, right? Does Bayesian evidences prefer asymmetric transit models to our symmetric transit models, either in a white light standpoint or as a function of wavelength? And so I think by kind of having the community start doing these tests more regularly, right, we can have a little bit more faith in the limb asymmetries that we're potentially observing, especially as they become more borderline and not necessarily as very kind of in your face clear as some of the previous observations have been. So I think in the interest of time, I'm going to skip over eclipse mapping. So I apologize to all the eclipse mapping fans here, but once again, I'm by no means an expert in this field, and there are a lot of people here that know eclipse mapping a lot better than I. And so I'll give them the opportunity to perhaps talk about this in a later seminar. And so, yeah, just to conclude of what I've talked about, right? Planets are obviously 3D, but 3D effects have been very difficult to observe in pre-JWST observations, either due to phase curves being simply photometric observations and it being difficult to disentangle reflected light and thermal emission, or HST observations with their big gaps between exposures being very subpar, for lack of a better word, right, to actually get limb asymmetry signatures from that very important ingress and egress domain. However, JWST has really changed the game for this. And ultimately, phase curves still remain that gold standard, but are obviously very time consuming. And so detecting limb asymmetries during transit is a very good time efficient manner to assess 3D effects in planet atmospheres. And we've had many success stories in the JWST era: WASP 39, WASP 107, WASP 94, and Wongwei's paper recently, which I have not yet read because I'm nominally on vacation for this week. Also, I think had added WASP 17 to this pool. WASP 96b might also be joining this club, with evidence for a cloudier morning and a cloud-free evening hemisphere. But this is very much a borderline result here. And as I think a field, we need to be a little bit more thoughtful about how we can actually assess the robustness of these transit asymmetry signatures, especially in borderline cases. And I propose here that these kind of ensemble approaches might be the best way forward. So yeah, thank you everyone for attending, and thank you for listening, and I'll be happy to take any questions.
Thank you very much, Michael. If we have questions, so we can either raise your hand or also type in the chat, and I will read out those questions. So Tad, was that a question from you?
Oh, it's just the applause, but I do have a question. Though we should definitely focus on early career people, but I guess there'll be enough time. There's 10 minutes. Yeah, my question is, it seems very common that we see limb asymmetries in nearest sauce, but we don't see asymmetries in near spec for the same object. And I was wondering if you think that might be instrumental or if that might be physical, for example, telling us something about the characteristic aerosol particle size in these atmospheres.
Yeah, I think my initial assumption, right, would be from the instrument standpoint that it would be easier to get limit symmetries out of a near spec observation than a nearest observation. The reason for that being, in general, right, you have shorter integration times with near spec, you have more integrations in your ingress and egress, which should make detecting limit symmetries easier. So the fact that we see more in nearest, or it's starting to look like we see more in nearest than in near spec, I think kind of shows us that it's probably just that there are more easily observable limb asymmetries in those more optical wave bands. Kind of like the same thing, right? Where with right, kind of in the opposite regime of the bias, right? If we saw more in near spec, that could conceivably be kind of just an observational, easier to observe bias. But the fact that we see them more in nearest, yeah, I do think is actually a physical thing. Could also be because cloud formation and aerosol being present, probably more easier to observe with nearest, especially if you're doing just like a G295 with near spec, where then you're solely more sensitive to temperature and chemistry differences. So that could also be another thing. But yeah, my gut is that this is kind of a real underlying astrophysical thing and not just an instrumental bias.
Interesting. Thank you.
Do we have any more questions?
I do. Sorry, I'm just trying to unmute and turn my camera on. There we go. If you don't mind. Michael, great talk.
Thanks.
I really enjoyed it. I have two questions. The second is not very well formed, and it may be just me thinking aloud. So I'll go with the first one first, which is, and I may have missed this, but when you were showing your fits to the WASP-96b spectra in your IMPREP paper, you sort of had that the cloud composition was Na2s. And I was curious whether or not that was based on a spectral feature or whether that's based on just the cloud species you'd expect at this temperature.
Yeah, so this is entirely based on, just we twiddle expect Na2s clouds to form on the morning hemisphere. We're not really sensitive to whether, and this is kind of why I've been careful to say, right, aerosol and not necessarily cloud or haze, because effectively what we just have is that slope towards the blue, which could in theory be reproduced either by a haze slope or by me scattering clouds. We don't see any specific features that would say Na2s versus ensitite versus KCl versus anything. And realistically, right, whether I choose KCl, whether I use ensitite, force-right, et cetera, kind of any of your normal cloud condensates, they all fit the spectrum equally well. So we can basically say there is some sort of me scattering cloud with particle size, I can't remember exactly what offhand, or perhaps a small particle haze slope scattering. But yeah, it's not really like we can definitively say it is a cloud or a haze or even a specific cloud condensate.
Yeah, that makes sense. Thanks. And then the second part, which is not the not well formulated part, was motivated by what you were saying at the end about sort of trying to encourage the community to come up with this sort of set of criteria, basically, to interpret whether or not limb asymmetries are sort of warranted by the data or not, which kind of got me thinking about this Bayesian evidence, and also in consideration with Evie's WASP-94 limb asymmetries compared to Shagnick's. And like you said, by eye, it looks like Evie's shows these asymmetries, but ultimately the Bayesian evidence doesn't support that. But I was sort of wondering, in terms of the Bayesian evidence, that if you're sort of fitting these models and you're assuming that there is no limb asymmetry, then there's no prior information that is supporting limb asymmetries. But if you use a prior that is motivated by GCMs, for example, for this particular planet, and you would expect that there would be limb asymmetries of a certain degree, then presumably that could swing the Bayesian evidence in favor of limb asymmetries. But I don't know whether, that may be as statistically like, you know, a bad thing to do, because you're kind of like essentially trying to force it to look for something that you're hoping for, rather than just letting the data speak for itself. But I you know, I don't know, but maybe it's something to think about. And
yeah, I think you could even maybe do a similar things like kind of your odds ratio test as well. Like normally, right, you assume kind of the prior weight for model 1 versus model 2 is equal and just compare your evidences. But, you know, maybe there's some room for, if GCMs really robustly predict limb asymmetries, that you can tweak those model priors. But again, yeah, maybe, I think, like I said, it's something that I think that as a community, right, we need to think a little bit. We need to be a little bit more thoughtful about, and maybe there is a better way to do this than simply assuming that the probability of there being versus not being limb asymmetries is equal. And maybe there's a better way to like weight the model priors, for instance, when you're doing your Bayesian evidence comparison. But yeah, you also then obviously risk biasing your statistical outcomes to things that maybe you want to occur as opposed to what's actually there. Yeah.
Yeah, really interesting. Thanks for prompting this discussion.
Thank you. We maybe have time for one more quick question. Anyone's? Okay. Otherwise, I think we should thank Michael again. Thank you very much. And
thanks for having me.
And just a reminder, the next of our Bowie seminar series will be on the 28th of August. And enjoy your vacation, Michael.
Thanks.
Okay.
Take care, everyone. Thank you again.